Paris 6 or 7, whatever. 6 probably.
It's Paris 6, yes, Paris 6
yeah,
now.
Paris 6, and he will speak on the categorification problem for motivic DT-invariants. Okay, please.
Okay, so thank you very much for this invitation, for allowing me to explain these results. So this is a working project. So this, I should stress the part in progress, and it's a collaboration with Benjamin Hennion, it's in Orsay, and Julian Holstein from Hamburg. So I'll try to explain you the results we already have and the results we are now trying to wrap up and write all these details. So I started by preparing a small introduction to DT-invariants. I think most people here won't need this introduction. I would need this introduction for myself. I think all you probably know this much better than me. So anyway, I have this slide. I'll pass it fast. And then I will explain this shifted symplectic forms business. I will explain the gluing problem, what we're actually trying to do. And then the last 3 parts, I will explain how we try to do it. Okay, the strategy for this gluing problem, all these last parts. Okay, so for DT-invariants, so the setup is the following. We start with the Calabia variety. So this is what we want to study. So Calabia in this talk just means an algebraic variety, threefold over C, with the trivialization of the canonical bundle. So that's all we need for this talk. And just as a quick example, if you take the Fermat quintic, so we know this is Calabia because of this junction formula that allows us to compute the dualizing sheaf from the structure sheaf. So in this case, we have for any quintic we have this formula. So this gives you an example of such a Calabia. So as more as a motivation, I'm sure people here know all about this much better than I do. So as a motivation, I try to give a slide to explain slightly the prehistory of this subject as I learned it. Probably it's not the best way to tell it. I don't know. So in physics, there is this Kaluza-Klein models, which essentially says that, so this dates back from the 1920s, where Kaluza and Klein tried to explain electromagnetism and gravity as in space-time as just pure gravity on this product. So they introduced this space here, this copy of S1, R4 times S1, and they came up with this observation that pure gravity with an extra dimension becomes gravity and electromagnetism in 3 dimensions. So fast forward, if you want to take in consideration the other forces, and if you fast forward, there is this observation by Witten, Candelas, Horowitz, and Strominger, that in string theory, if you want to play the same kind of game, the manifold you have to introduce here has to be Calabia of dimension 6 real. So again, the idea is the same, is that physics in R4 comes from the geometric properties and topological properties of these extra dimensions you put here in this Calabia. So this is just kind of the basic idea, and the reason why you want Calabia is to do with physics in the end. So the other idea is that as particles or string particles move into space-time, we see the strings moving, so they create these Riemann surfaces or just one-dimensional algebraic curves. So if you want to do physics, you want to compute some amplitudes of these particles moving, you actually have to compute the numbers of curves inside the Calabia. And that's kind of how physicists enter this enumerative geometry business. And this brings us to this problem of counting these curves. So counting curves in a Calabia, we have these 3, I'm going to mention 3 different approaches we can take. So the first approach is to count just parametrized curves inside the Calabia. And these are as we know, these are Gromov-Witten invariants. So more precisely, what we do in Gromov-Witten theory is we look at a stack of stable maps. So stable maps mean maps with a finite number of automorphisms, where we fix beta, the class of the curve, in the homology of Y. We fix the number of points and we fix the genus. So the idea is that if you want to count these curves, what we do, in fact, is we try to compute the volumes of these spaces. In this case, the volume is well defined because this space happens to be quasi-smooth, or actually in more down-to-earth terminology just means it's LCI, it's a local complete intersection. So we can compute the volumes, and these volumes make sense, and they give rational numbers, and these numbers are the Gromov-Witten numbers. So I don't want to explain this here in more detail. I just want to see how the Donaldson-Thomas appear from these logics. So the second approach we could try to do to count curves would be to count embedded curves, not all parameterized curves, just embedded. The problem is that this would take us to study the Hilbert scheme of codimension 2 subschemes in Y. And since we are taking all curves and not just LCI curves, this moduli space is not quasi-smooth. So in particular, the volume is not well defined. So if you want to count curves, embedded curves, the other way to try to do it is to replace the study of the embedded curve by the associated ideal sheaf. And this is where the Donaldson-Thomas invariants come into the picture. What we try to do, and I'm lying a little bit here, but what we try to do is to compute these sheaves. We look at coherent sheaves on Y, and we want to count them. And in this particular case, what we do is like we look at the moduli of coherent sheaves. I should maybe plug in some specific hypotheses, some stability conditions to make this moduli space behave a bit better. But anyway, so this is the idea. We want to look at this moduli of coherent sheaves. And the difference with respect to the Hilbert scheme before is that even if it's, sorry, is the question?
No, I don't think so.
Okay, so the difference with respect to the Hilbert scheme before is that even if the underlying points are the same, the deformation theory is a bit different. The deformation theory of coherent sheaves happens to be quasi-smooth, or LCI. And the reason for this is because one, the variety is a Calabia variety, and two, because of Serre duality. So the Serre duality rigidifies the deformation theory of coherent sheaves, and it happens that these volumes now exist and give integers. So this is the perspective we have for this talk on Donaldson-Thomas invariants. We want to compute moduli volumes of moduli space of such moduli space of coherent sheaves. Okay, so let me maybe start more the talk, like where the direction I want to take it. So the first observation, as I said before, is that the combination of the Serre duality and the Calabia condition imposes some rigidification of the deformation theory of coherent sheaves. In particular, it imposes a symmetry. So it imposes the following relation. If we look at first-order deformations of a given coherent sheaf, this space is actually dual to the space of abstractions to deformation of that same coherent sheaf. So abstractions and deformations are in dual relation to each other. And this comes from the Serre duality and the Calabia condition. So this duality gives a specific structure to the deformation theory. And it was observed first by Kai Behrend that if you take a stack which exhibits this kind of symmetry, like the space of first order deformations is dual to abstraction to the space of abstractions to deformations, then, so an example would be this moduli of coherent sheaves on a Calabiao. Then there's actually another way to compute the volume of the moduli space that comes from the definition of a function called the Behrend function, and that essentially allows us to break the moduli space into to stratify it and then compute the volume by computing the volume of the value on the Euler characteristic of these of one species of this stratification for the Behrend function. So
did he consider algebraic stacks or just schemes?
I think he actually considered algebraic stacks, but I'm not sure if it was in an original paper or later. I'm not sure.
I remember that something that he considered schemes only, because when you ask for stacks with some quasi-smoothness conditions, so it's natural to ask what will happen for more general stacks, but I don't think it was really this question was posed at his time. Yeah, so
Yeah,
but it's just historic remark. I'm not,
yes.
I'm also not sure.
You're probably right. When I wrote these slides, I tried to write it to optimize it for the talk, and probably I lied a little bit. I would have to confirm the original paper. I had, okay, yeah.
And integral means integral of one.
Mean of one or the fundamental class. Here I'm integral of the virtual class. The cup product in homology.
But which function you integrate?
No. I just take the virtual.
It's a notation.
Class. Okay. It's a notation for the cup of the virtual fundamental class in homology.
Okay.
Yeah.
Okay. Mm-hmm.
So, yeah. So the idea is that we have these two ways of computing this volume. One using this virtual fundamental class that Behrend defines with Fantechi in the data paper, or using this function. So yeah, so what I want to emphasize here, and I will come back to this Behrend result in a second, what I want to emphasize here is that behind the scenes, what is happening is that this symmetry in the deformation theory that allows Behrend to construct this function is actually just a residue or a shadow or a way to see the existence of a -1 shifted symplectic form on the modular space of coherent sheaves. So this was later observed by Pantev, Toen, Vaki, and Vezzosi in their paper on shifted symplectic structures. So, and this is the direction I will try to pursue in the talk, is that from this perspective, the symmetry that allows the Donaldson-Thomas theory to make sense comes from this -1 shifted symplectic geometry. So I'll come back to Behrend's function in some slides. For now, I just wanted to make a quick survey of -1 shifted symplectic forms. Well, very briefly, so the idea is that if you have a stack, let's say an algebraic stack, but any derived stack is controlled by the deformation theory is controlled by the cotangent complex, which is an object in this derived category of X. So the moment you have this deformation, this cotangent complex, you can actually ask yourself when it is dualizable. So, and every time X is a finite presentation, this complex is dualizable as a complex, as a perfect complex. So the dual, let's just call it the tangent complex. And what happens is that, for instance, when X is smooth, we know what this is. It's the easiest case. It's just the Kähler differential forms. It's concentrated in degree 0. And in this case, we can define, if we have this cotangent complex or tangent complex, we can define two forms simply as global sections of this wedge product or bilinear forms on Tx. So in particular, we can also define shifted two forms or n-shifted two forms where we just ask for, we want to touch cohomology classes in this complex in the global sections, which are in degree n. So this is just a definition. And another thing we can ask is the existence of the Durham differential for such kind of shifted forms. So the Durham complex in this case, it also exists. It's we have to be careful because now OX is itself a complex, LX is itself a complex. So this is somehow a complex of complexes. And what Kohn and Toen Vezzosi tell us about this is that we should actually understand this de Rham differential not as an internal differential of a bicomplex, but rather as an action of an operator of degree 1. So it is this change in perspective that will allow us to make many definitions work in this shifted symplectic geometry. This difference between being a bicomplex or just an extra operator. So
May I ask you, can interrupt you?
Yes.
So when you say a derived stack sets of arbitrary nature, for example, if I take something like a three-dimensional Calabia category, which is a Fukaya category on something, and take the stack of objects,
yes,
will it fit into
it will
this?
fit. It will fit, yes.
Okay.
If the category has it's depending on the finiteness properties of the category, it might be algebraic or not, but it's going to be an algebraic stack or not, but it's going to be typically of finite presentation.
Okay, so
it's going to have
this
a
is volume. Okay.
Yes, this is where we are going somewhere in some sense. So yes, we can talk about this now. Once we have the de Rham differential, we can talk about this n-shifted closed to forms. So what is a closed to form? So a closed to form, we have heuristics for what it should be. It's just a form whose de Rham differential is 0, or in this case, homotopic to 0. So what we do is we play this game where we're gonna look at K. So this is a heavy notation, but it's easy to understand. So you have K, this is K. Can you see my mouse moving on a slide?
Yes.
Can you?
Yes. Yes.
Okay. So when this is K, the degree 2 here just means that I put K in weight 2 because I want a 2 form. And the shift, let's forget about it for a second. Let's just suppose it's a 0 shifted form. Okay, forget all this part. Forget this. So what I'm doing is considering K with a trivial de Rham differential, so the trivial epsilon action, and I want to touch an element of weight 2, so meaning something that lives here, and with the de Rham differential. So by touching an element such like that, I'm essentially asking for this equation to be valid. Such maps are equivalent to a pair omega and an homotopy between the Rham of omega and 0. So it's just a way to encode this information as maps of these things are called mixed graded complexes, and these are just maps of mixed graded complexes. So I have a way to plug in a definition of n-shifted close to forms. So in particular, I have a way to talk about shifted symplectic forms. I mean, I don't have a way. Tony Pantev, Toen, Vaquier, and en-Vezzosi introduced this way, which is to look at, if I have a stack, an n-shifted symplectic form is an n-shifted close to form, so something that I just mentioned, but where I ask that the underlying form, so the underlying 2 form is just something like this, a bilinear form which touches something in cohomological degree n, is non-degenerate. So by this, it means that if you look at the map induced on the tangent, from the tangent to the dual, which is the cotangent, this map, you ask it to be an isomorphism, exactly as you ask for the non-degenerate condition on a symplectic form. So this is a definition, which is, here it seems simple, but actually this closed structure is what makes the definition very, very heavy on structure. And the moment we have this, so I can give 2 examples or 3 examples. So the first example is a 0 shifted symplectic form. I just look at the T star of A1, it's A2, and it has the usual symplectic form that you would easily guess, of course. So this is 0 shifted. Another less trivial, way less trivial example is a stack that classifies perfect complexes. So maps from something to this stack is a perfect complex on that something. So this has a 2 shifted symplectic form. So how do we see this? So if you have a perfect complex, the first thing, like say you have a vector bundle, okay, E is a vector bundle. So the tangent space of a vector bundle, the deformation theory is just endomorphisms of the vector bundle with the sheaf by one. This is a classical deformation theory example. So since it's a vector bundle, it has a dual, so I can just write it this way. And in this case, I can tell you what the form is. The form is just, so I just smash it with itself. So I just get a copy of this. So it's E tensor dual, tensor E tensor dual. And what I do, I just use the evaluation map from the pairing E dual. So I compute essentially I'm computing the evaluation map, or it's the I can use the symmetry or so this map is the symplectic form on the stack of perfect complexes. So another example is also given by Kontsevich and en-Vezzosi is the following, which is what we want in this talk. So I take a Calabia variety of dimension 3 over K. K is C here. Then I can look at the mapping stack. So the derived stack of maps from Y to perf. So perf is the derived stack. I take maps in derived stacks. So in this case, the theorem tells us since Y is Calabia of dimension 3, and since perf is has a two-shifted symplectic structure, the theorem tells me that the whole thing, the map, will have a 2 minus 3 equals minus 1 symplectic structure. So this is the thing we want to focus in this talk, because since Y is smooth, I can actually identify the moduli of coherent sheaves on Y, because coherent sheaves, the classical coherent sheaves on Y and perfect complexes on Y coincide in this case because of Serre's theorem for smooth things, smooth varieties. So in this case, I can actually identify the moduli of coherent sheaves on Y as an open substack in the moduli of perfect complexes on Y. So this is an open. It's also minus 1 symplectic because it's an open, so I restrict the symplectic form. So the claim is that in this case, I recover exactly the Behrend symmetry that I mentioned before. So maybe you want to see why you recover the Behrend symmetry. So I will give you an example, very explicit, where you can see that the minus 1 shifted structure keeps exactly track of the kind of symmetry that Behrend observed first. So let me give you this example. Suppose U is a
so what
yes.
do you call symmetry which Behrend observed first?
So the fact that the space of deformations is is dual to the space of abstractions to the existence of the deformation.
I think it was first observed by Thomas in his thesis.
Okay.
This is why it's Donaldson-Thomas invariants. Yeah.
So I apologize for that. I didn't know that. Thank you.
Yeah.
Thank you for correcting me. Sorry. Okay. So let me let me show you an example where you can see what is going on. Very simple. So take a smooth scheme and take a function and look at the derived critical locus. So if you don't know what a derived critical locus means, you can just think about it as you can look at the critical locus. Okay, so you just look at the points where f prime df equals 0. But this time you're going to build a causal resolution, and you keep track of all the algebra structure on the complex and the algebraic structure on the causal resolution. That's the functions on the derived critical locus. And the thing is that if you try to compute the deformation theory of this derived critical locus, I can present the computation for you. What happens is that the tangent complex of this derived critical locus lives in 2 degrees, degree 0 and degree 1, and the derivative, the boundary map, is the Hessian of f. So this is a computation we can do. If you want, I can tell you how to do this, but this is simple. And the moment you have this, you also have the cotangent complex. The cotangent complex is just a dual. So when you dualize, you're going to have something degree -1 this time, and you're going to have the dual of the Hessian. But since the Hessian is symmetric, what happens is that actually one complex is just a shift of the other by -1. So this is the symplectic form that appears on X on the derived critical loci. So it's just this, and the fact that this symmetry that Thomas observed is just the fact that every time you have a complex like this, H0 and H1 are actually dual. If you compute H0 of this complex and H1, you get the same thing with the dual. So that's the symmetry observed. So okay, so why do we care about this particular example, if not for illustration of the symmetry? So okay, so this is the two form. So just before moving on, let me tell you an example, a simple example where you can compute everything by hand very easily in 5 minutes. Is just you take a smooth scheme A1 with the function x cubed, and you show that the derived critical locus is actually underived. And you can actually compute that in this case, what you get is just multiplication by the Hessian is just multiplication by 6, and you can do all the computation explicitly to convince yourself of what is going on here. So why do we care about this example? Because of this theorem due to Joyce and his collaborators that tells us that, so is determined by Brav-Bussi-Joyce, and that tells us that all -1 shifted symplectic schemes are Zariski locally of this form. So all -1 shifted symplectic schemes locally, Zariski locally, you can find a symplectomorphism to a derived critical locus. So that's the starting point essentially of this talk. I will try to explain you now why this is important. I'll come back to Behrend's result also. So a consequence of this is that locally on every -1 shifted symplectic scheme, you can, since you have, locally you can define a U and a F, you can look at the sheaf of vanishing cycles for this U and this F. So you can look at how the F, how F is essentially these are sheaves on U that will tell you how much F is not a smooth map, and these are actually perverse sheaves. So with support on the critical locus, but since we have this Kashiwara lemma for the modules or perverse sheaves, these are just perverse sheaves on the critical locus. But perverse sheaves do not see the derived structure, so it's just perverse sheaves on the underived or derived is the same thing. So locally, we can try to isolate the information of these perverse sheaves. So the problem is that Joyce does not tell us, this theorem of Joyce does not tell us that these U and F are unique. So here is an example where you see that the same derived critical locus, the one I wrote on the left, on the right, are actually given by different smooth schemes, U. So in this case, this is A1, this is A2, with different functions. So there is an ambiguity that you have to keep track here. That can give that a priori give the same derived critical locus. So the U and F are not unique. So this is the and in this case, what happens is that although the vanishing cycle sheaves are isomorphic, this isomorphic is non-canonical. It depends on the choice of an orientation somewhere. So well, so this is the starting point. So let me go back to another theorem now of Brav-Bussi-Dupont-Joyce-Szendroi. Let's say it's the following thing. So if I have a -1 shifted scheme, and I assume that there exists a line bundle together with an equivalence, L tensor L isomorphic to the determinant of Tx, so the canonical bundle. So this is called an orientation data. Then these locally defined sheaves glue to a globally defined perverse sheaf on X. So that's the first statement. So the existence of these possible local ambiguities in the definition of U and F is somehow solved. And the second thing is that if I compute the Euler characteristics of this sheaf, I get back the function of Behrend. So
did they consider only derived schemes?
So no, they have two different papers. One paper where they consider schemes, and one where they consider arting stacks.
Okay. Because actually it's kind of, there are many kind of smart words, but if you, I mean, it all goes back to our paper with Maxim of 2008, where we consider inconstructible three Calabia categories, and the square root of the this determinant bundle is just that of X groups for three Calabia. So it's kind of, it looks pretty abstract, but it can be done in a very down to earth language. So
I would really like to, I want to understand how exactly this is related. So the reason
I mean, I'm pretty sure that, I mean, I did not try to kind of to follow all these definitions, but if you have a three Calabia category, you have a third duality in dimension 3, of course, and you have what is known as determinant of R gamma. So it's like you construct a line bundle on the stack of objects with the fiber, which is a tensor product. It's like determinant of x0, tensor with determinant x1 in the power -1, with product determinant x2 in the power 2 and x3 in the power -1, something like that. All even determinants goes in the numerator, all odd in the denominator, whatever. And so this is a line bundle, and it's like a spin structure on the stack. So if you want to resolve, you should find, you should choose the square root of this line bundle. I mean, really to define the spin structure. Yeah, and this is a choice of your L in this abstract language. I mean, it's all including the construction of the sheaf of vanishing cycles and all of that paper. I know that Joyce doesn't like to cite our paper, but in fact, it's all in it, including actually the construction of motivic version, which they didn't do, because this Behrend function is some quasi-classical limit of a more fundamental object. I mean, the original Behrend function, which was related to enumerative invariants, not to motivic. Well, anyway, so I mean, I'm surprised that people kind of cite this Joyce and other paper without seeing that all that was done before. You just should combine it with the language of shifted symplectic schemes of Pantev and other people. Yeah, but you see, like this, and even this language of shifted symplectic schemes or stacks or whatever, it has a pretty geometric description, which was known to physicists. It's known as BV Batalin-Vilkovisky formalism. When your Derived differential is just interpreted as a vector field of degree +1. So then, anyway, I don't want kind of to disturb your talk too much, but
can I just say one word?
Sure. I mean, you'll say many more words.
No, about the specific choice of this presentation of the orientation data. The reason why we chose this particular presentation is because when we want to glue the categories, the orientation data, these orientation data will not be enough. And understanding it this way helped us in particular to understand what kind of orientation data we needed. So I will come to that. And if you have comments on that, I would really like to hear your comments.
Yeah, great. But here there is no specific choice. You just choose any orientation data, which is this line bundle. But then, of course, if you'd like to glue the constructible sheaf on the stack of objects on your derived stack, yeah, you should be more careful.
So I hope I will.
Yeah. Okay. Go ahead. Sorry.
Okay. So this is their theorem, as you just commented. This theorem has a long history, as you also just said. So the idea essentially is that these locally defined vanishing cycles. So locally, this function gives you the Euler characteristic of vanishing cycles. So which gives back the DT counting. So the proof of this that Joyce and his collaborators give in the paper is essentially achieved by gluing local presentations of your -1 shifted scheme as classical critical loci. You glue and you solve the ambiguities by hand of how these possible ambiguities in the choice of U and F exist. The problem with this method, well, there are several problems it has if you want to apply it as we wanted to apply to glue something else. So the first thing it does not see the derived structure. And the strategy work if you want to glue perverse sheaves, because perverse sheaves essentially form a one category. If you want to glue something which has a bit more homotopy, it won't be enough. And the other thing why it also works, it's because the perverse sheaves have the A1 homotopy invariance property for morphisms. So I will try to give a few words about these things in the end. So, but these are essentially the three essential ingredients that make this particular proof of Joyce work. So now let me explain you what we try to do. So as I said before, the basic pieces that we care about are these derived critical loci. So if you have an U and an F, you can try to look at the different invariants that capture these vanishing cycles information. So the first is this perverse sheaf of vanishing cycles. The second one would be to look at the motive of vanishing cycles. So this is just an object that lives in motives. So in Vervotsky motives, I mean, and then it has a particular, so this object, the one I'm mentioning here was constructed by Ayub, Joseph Ayub, and has the property that after realization, it coincides with the perverse sheaf of vanishing cycles. So the battery realization. And there are other objects we could consider. So one other object would be and will be these derived categories of singularities introduced by Eisenbud, Orlov, and so these are categories, DG categories, which happen to be two periodic. And I will explain in a few words why they are two periodic. But the thing is, all these objects that are here are related in the sense that, well, the motivic vanishing cycles after realization give the perverse sheaf. And these DG categories, by results of Efimov and Claude Sabat, if you take the periodic octal homology of these DG categories, you also get the information of vanishing cycles. So this arrow is a bit of a lie, but that's essentially the direction in which it goes. You don't recover exactly the vanishing, the perverse sheaf. You recover the global sections of this perverse sheaf.
Mark, I'm a bit confused. You consider like perverse sheaves and motivic, whatever you need, motivic vanishing cycles for what? For Artin stacks or?
No. Just for a smooth schema and a function F.
Great.
Yeah, this is just a smooth schema and a function, and I'm just describing different invariants that we can extract and that capture the information of the singularities.
Okay, good. Thank you.
So it's just a very simple. There is nothing in this board that you don't know. It's just I just wanted to emphasize that there is another way to complete this diagram. You know, the work we did with the Blanc, Owen, and Vezzosi, and now PP, where we show that actually these motivic vanishing cycles of Ayub can also be computed from this MF. So this category is MF. So MF is really somehow some very basic object we can consider that still gives all the information of vanishing cycles we knew before. And this is one reason why we're interested in these categories MF. So why they are two periodic? So the reason is the following. So let's take a scheme U with the function f, and let's look at the zeros. Let's call U0 the zeros of this function. And the thing is, U0, if f is not smooth, U0, every coherent sheaf on U0 will have an infinite resolution by projective modules. So if U0 was smooth, all resolutions would be stopped. I have a finite number of steps by Serre's theorem. But if it is not smooth, it will have an infinite resolution. But because of this, there is a result by Serre, Osland, and Buxenbaum formula and Eisenbud. What happens is that this resolution eventually becomes too periodic after a while. So essentially what this category MF captures is only the piece of the resolution that is too periodic. So we keep all coherent sheaves, we mod out perfect complexes, and what we kept is just these pieces of resolutions which are too periodic. So this is the categories of matrix factorizations. That's the main insight to define them. We only care about such objects. So this forms a category. These resolutions form a category. And now we can ask the following question. So let's suppose we have a -1 shifted symplectic scheme. Locally, we have these pairs UF that are defined. So the question is, can we glue these locally defined DG categories, two periodic DG categories, as a sheaf of DG categories on X? So we want to replace the gluing of Joyce perverse sheaf by a gluing of DG categories on X. So this is the problem that we are trying to describe in our paper, in our work. So the first question is this Joyce orientation that we just discussed enough to glue these sheaves? And the answer is no. I will tell you why in a second. So this is also somehow similar to another problem in mirror symmetry, to gluing Fukaya category from local pieces. So I'll not have time to enter in details about this. It's just something people keep telling us, and it's something that we have to really look into. We didn't have time, but if people here are more mirror symmetry experts, maybe they will, I hope I have some comments on this. So other complications with the gluing. So is that the gluing this time no longer takes place in the one category, but in the infinity category, because the category of DG categories is an infinity category. So it's complicated to perform the gluing. So we need some idea to glue. We cannot just glue by hand. So this problem brings us to the first thing we consider, the first idea we considered, which is the Darboux stack. So what is the Darboux stack? So let's just, I'm going to make a fast review of the classical picture in symplectic geometry. So if you take a classic symplectic manifold, and then you know by the Darboux lemma that X is locally symplectomorphic to some T star M. So essentially the Darboux stack is going to be something that will analyze the moduli of such local identifications of X with T star M. So as a functor of points, you do something like this. For every open in X, a classic symplectic manifold, you assign the classifying space or the space of all symplectomorphisms from S to T star M. So this is just an heuristics. In a zero symplectic case, it's not exactly what you should do, but it's going to be a very good heuristics for what we do in a -1 case. So we look at this moduli stack, so this moduli functor, let's say. And the thing is that if you have a symplectomorphism of an open S in X to T star M, you can look at this in another way. So the fibers of this projection define you a smooth Lagrangian foliation on S. So if you have a T star M, you have to use a projection to M, and you have a fibration, a foliation of T star M which is Lagrangian. So the form is 0, restricted to the fibers. And the other thing is that the form is necessarily exact on S, because the form is exact on T star M. It's just a Liouville form on T star M. So we call this pairs F a foliation and alpha the exact structure Darboux data on S. So S is an open in my X. So what we will do is essentially try to look at this Darboux stack first, observe that it forms a stack, and try to study this stack in the -1 shifted symplectic case. So in -1 shifted symplectic geometry, this notion of foliations makes sense because of some recent work of Hennion and Vezzosi. They define derived foliations on derived stacks. And we have the following theorem due to Tony Pantev and Bertrand Tohen that says the following thing. So let S be a -1 shifted symplectic scheme. And then the following data, types of data are equivalent. So first, it's Darboux data, meaning exactly what I said before, a derived Lagrangian foliation on S plus an exact structure. Okay, so I can define what is a derived foliation. I can define what does it mean to be derived Lagrangian. So there is a lot of information hidden in this phrase. And this data is equivalent to another thing, which is the following. I have an exact structure plus the data of a Lagrangian fibration from S to U. So it's a fibration whose fibers are Lagrangian. And I ask that on the reduced, this is an isomorphism. So in particular, U will be a formal scheme. Okay. So what we try to mimic here is that the U is essentially the leaf space for the foliation that I define here. So if you have a foliation F on S, you can take the leaf space F S mod F, and this is my U. And another thing that corresponds to this type of data is exactly a symplectomorphism, an identification between S and the derived critical locus of a function on a smooth formal scheme. So local models given by D critical loci are exactly the same thing as derived Lagrangian foliations plus exact structure. So that's the upshot of this theorem. So in a classical picture, in a zero symplectic picture, Darboux's data on S would be just an identification between S and T star M, on a tau map from S to T star M. In this -1 shifted symplectic picture, the Darboux data on S is an identification of S with discrete and an inclusion with U. So the claim is that essentially this map, this inclusion of the derived critical locus inside U, is always a Lagrangian fibration, and the fibers, and the leaves, the fibers form a Lagrangian foliation.
So excuse me, I somehow lost in these many words.
Yes.
So if my critical locus is not derived, just as
It has.
in your toy model example, like function x cube. So
yes.
the derived locus was not derived, and it
right.
just so why it should have a symplectic structure?
It has, in that case, it has a symplectic structure, because if you see the symplectic structure, even in that case, the derived, so the cotangent complex is, as I said, is so I can go back. Wait, I can go back. It's going to take some time.
So what should I do? Look for perfect complexes or the
wait,
the algebra?
I think I'm going to get lost, but let's see. I have the, yeah, you see here?
Here
no,
it is. Yeah.
Here.
No,
no, it was not here. It was way before. It was here.
No, that's okay. You can.
So in this case, what happens is that KTU, you want to have to put, U is a 1, right? So you have KU, but you have to pull back to the critical locus. It becomes just K epsilon. This is K epsilon.
Yes, yes.
So you have K epsilon, and the Ashen is multiplication by 6 epsilon. So even in this case, right? In this case, you have K epsilon multiplication by 6 epsilon. That's Ashen is 6x. So even in this case, the symplectic form is non-trivial.
Yeah. Okay.
Okay. So and the inclusion this time, that's the trick. You have to replace U by the formal completion of 0 in A1. So the critical charts will no longer be algebraic. They have to be formal for the statement to work.
Okay. All right. Okay, good. Thank you.
Okay. So let's see if I can move fast forward. Yes. Yeah, this slide is very dense. There is a lot of words. But the idea is that the upshot is that every map like this corresponds just to a Lagrangian foliation on S. There's a bijection between Lagrangian foliations and maps like this, where U will be the quotient space, the leaf space of the foliation. Okay, so on the function you recovered from the difference between the exact structure and the isotropic structure. But I don't think this is very important. I think so. This is just 3 different ways to describe what this Darboux stack classifies. But if you just think of the Darboux stack as being locally classifying identifications of your scheme with the decrete of something. So an example. Oh, sorry, I forgot I had this example right after. So the example I just described would be this. Right, this map. So the claim is that this map is a Lagrangian foliation, is a Lagrangian fibration for the symplectic structure I just told you. So here's the construction. So if you take S anything et al over X, so X is a -1 shifted. So in particular, since it is et al, S is also -1 shifted. You consider the assignment given to every S. Sending it to the space that classifies exact structures on S and the smooth Lagrangian foliation. So this is called the Darboux pre-stack. And the claim is that this defines a stack on the small et al side of any -1 shifted derived symplectic scheme. Doesn't have to be even -1 shifted. So this assignment exists and is a stack for every n shifted guy. So I should put construction / proposition. So we called it the Darboux stack of X. So as a stack, you can actually decompose it as a product, is the product of the stack of the classifies exact structures and the stack of classifies smooth Lagrangian foliations. So these are complicated stacks, but they exist. And a comment is that in the case where X is a -2 shifted symplectic, this description as the Darboux stack recovers the local data that is used by Borisov and Joyce and Ho and Thomas to glue Donaldson-Thomas invariants for Calabia fourfolds. So they also have local models, and their local models correspond to this. So in this language, local models for -1 or local models for -2 shifted symplectic structures correspond to the same information, an exact structure and a Lagrangian foliation. So so now let me try to speed up, because I don't know how much time I have. I don't think I have much time, actually, sorry. So I have to speed up. So let me speed up to tell you how we try to glue the DG categories of matrix factorizations. So in both cases, both Joyce and both to glue MF and both to glue the perverse sheaves, the Darboux stack is actually the natural beginning of the construction, in the sense that the perverse sheaf of Joyce is actually defined naturally as a map from the Darboux stack to the stack of perverse sheaves. So this stack perv X on every S et al over X gives perverse sheaves on S. So this thing sending a local model to the perverse sheaf. So this is a map of stacks over the et al set of X. And the same thing works for the DG categories. So if I take a local model, a local presentation of my S, I can send it to MF. And this MF is a DG category locally defined. And there is a subtle point here, is that these MFs, if you want to glue them, you cannot just glue them as DG categories, which are k-linear. You have to glue them or as DG categories with a connection. So there is a connection that appears in the game that I will not have really time to explain. I can explain you if you ask me in the end. There is a subtlety with the k-linearity and that doesn't work. Anyway, these constructions are both defined on the Darboux stack. And now I can tell you at least how to recover Joyce and then how we go to our setting. So let me mention this action of quadratic bundles. And I mentioned it before that there was a choice, an ambiguity in the choice of local presentations. So I gave this example where the derived critical locus did not change when I added a function, a copy of y squared. So I copy a1 with the function y squared. So this is just a quadratic form. So I will look at the stack that classifies quadratic vector bundles on S with the connection. So again, the reason for the connection here has to do with the connection for MF, which I will not explain. But in any case, just think of it as a quadratic vector bundle. So what happens now is that I can do the construction. If I have a -1 shifted symplectic drive scheme, then I can look at the stack that classifies quadratic bundles with the connection. This is a monoid because I can make sum of quadratic bundles. And this stack acts on the Darboux stack and preserves the critical loci. So exactly as in this example I wrote here, if I have a quadratic bundle over X, I can twist my add the quadratic bundle to U, another space, F plus Q, and I clip the critical locus essentially because the quadratic form does not have, the critical locus of the quadratic form is trivial. So by acting with quadratic bundles, I fix the critical locus. And the remark is that essentially every map of Darboux stacks, of Darboux foliations, sorry, so I can map of LG pairs if you prefer. Every map of LG pairs that fix the critical locus is necessarily of this form. It's U plus a quadratic form locally. So this is the way we solve the ambiguity by acting with quadratic forms. So now I can tell you our main results. So let me tell you how to recover Joyce from all this abstract nonsense I just described. So the first thing is that if you have a quadratic form and if you take the determinant, you get a line bundle which is 2 torsion. That's because you use the quadratic form to write down this isomorphism. And this is a consequence of the fact the Hessian is non-degenerate. So given this observation, I'll make some constructions. So the first construction, let's take X and -1 shifted symplectic scheme. Then you can look at the determinant map, sending a quadratic bundle to this 2 torsion line bundle, which is, I wrote this way. This is a stack classifying 2 torsion line bundles. So this is a map of monoids because the determinant sends the sum to the tensor product. The map that describes Joyce construction sending a Darboux presentation to the perverse sheaf is compatible with these actions in the sense that I just told that quadratic forms act on Darboux presentations. You just add the total space of the quadratic form. It fixes the critical locus. And in this case, you can also act on using a 2 torsion line bundle. You can act on perverse sheaves. And the claim is that this is compatible on both sides. So the action here is the one defined by Joyce. On this action of BU2 on perv is defined by Joyce. That's the one we take. And so in particular, since everything is compatible, it passes to the quotient. So we have this very complicated, with a lot of words, map of stacks, 2 quotient stacks. And this is the one we're going to use to recover Joyce. So let me state okay, this is just an observation that quad is not a group because you don't have inverses for the sum, but so we have to group complete. So I'm going to add plus. I'm going to even complicate even more this story by adding plus, the group completion. So now let me tell you how we recover Joyce from this story. X is -1 shifted symplectic. We have this quotient map. We claim that this quotient map is null homotopic. So that's the claim, meaning that it factors through the final object X, where we see X is the final object in the étale topos. So all these are maps of sheaves on the étale topos, where X is the final object. And the main claim is that this map of Joyce is null homotopic. So there is an homotopy that makes this diagram commute. And you see that such a map from X to perverse sheaves is mod mu2. What it is giving you is exactly the existence of a perverse sheaf mod a b mu2 action. In other words, the gluing of the perverse sheaf of Joyce always exists even without an orientation data if you are willing to pay the price of working in this quotient. So where does the orientation data plays? What is the role of the orientation data? So let me take the map I just described that exists, this thing that always exists because of the null homotopy. I take the projection for perverse sheaves to the point. So this class classifies me a line bundle on X, an element in H2 Z-mod 2, which is exactly the bundle classifying square roots of that 2. So following this observation, what this tells us that the orientation data that I described before, that we discussed before, is precisely a trivialization of this class. So a way to make this composition null homotopic, factor through the point. So the moment you fix such a red arrow, which is the orientation data, it lifts from perverse sheaves mod b mu2 to perverse sheaves, and you have one well-defined perverse sheaf on X. So this is how the orientation data appears in our description, and this is why. So in the end, the claim is that this p bar down here always exists. This blue dotted line requires the orientation data. So what we try to do to glue MF now, so very briefly, we try to do exactly the same game. So MF, if we take a quadratic bundle, you can take MF, which is a 2 torsion DG category, 2 torsion, 2 periodic. So 2 periodic it was already, 2 torsion comes from this Thom-Sebastiani theorem, tells you that MF of Q tensor MF of Q is MF of the product. And MF of the product, or every time you have something like this which has a Lagrangian inside, the diagonal gives you a Lagrangian here. You can identify with MF of the point of the base with the zero function. So this is last isomorphism is the Knorr periodicity. So every time you have something like this, you can do the same construction, replacing 2 torsion line bundles by 2 torsion DG categories. So you take X and -1 shifted symplectic derived scheme. Then you have the MF as a map of monoids, sending a quadratic bundle to MF of the quadratic bundle with this 2 torsion structure. You have MF, as I described before, from the Darboux stack to DG categories. Every local model is sent to MF of that local model. And the claim is that, again, all this is compatible with the actions. So it descends to the quotient. So you act with Azumaya algebras are just invertible DG categories. So every time you have an invertible DG category, you can tensor any DG category by it. So you can act. This acts here. So the claim is that all this descends to the quotient. So the corollary of this, so now let me be very careful because there are some dishonest corollaries and honest corollaries. So a dishonest corollary would be, we could try to do what we did with Joyce. The problem is we don't have the null homotopy on the nose. So if you willing to a certain price, let's say we fix a section of this stack, then we know how to glue MF. So it's not true that we know how to, sorry, let me go back. It's not true that we claim that this is null homotopic. What I'm saying is that if you have a section of this stack, whatever it is, then we can understand what kind of orientation data we need to glue MF. What is this orientation data? So first of all, we would need, as we had for perverse sheaves, we have a map from X all the way to this B as Umaya, 2 torsion, 2 periodic. And what we need is to trivialize this composition. So, but this information of this map from X to B as Umaya is too complicated. It has more classes than just the class of Joyce. So the upshot is that the orientation data that we had before is not enough to glue MF. So let me give you an idea why. So this 2 torsion is just the kernel of multiplication by 2. So what happens is that we're going to have several obstruction classes to the gluing. I'm going to write all of them here. So we had the class of Joyce that was the one solved by the existence of the norm of the line button square root of the canonical bundle. But now we have more classes we have to solve. We have 2 classes here that come from the existence of these 2 non-isomorphic isomorphic algebras. So this is essentially the 2 elements in the super Brav group, and the Z2 graded in the super Brav group, we have a class here that comes from this kernel, and then there is nothing. So there are these 2 new classes that appear, and that are not automatically trivialized the moment you fix an orientation, as in your sense of your paper and the paper that the definition I gave before by Joyce. So this is some important part of the message. And what about the gluing itself? So what we would like to say is to say the same thing we said for Joyce, that the map MF is null homotopic. But the way so Joyce, essentially our argument to reprove Joyce is to produce the null homotopy. But here is more complicated to produce the null homotopy. So what we're trying to do is to essentially go a bit further in this quotient, to simplify even further this quotient and prove it is isomorphic to X. We would like something like this map to be an isomorphism. So let me tell you what we have so far. So first of all, this stack, quad Darboux mod quad, its pi 0 is just exact structures on X. So that's the first result we have. And this is because the action is transitive. So that's the first result we have. The action of quad on Darboux stack is transitive. Second result is that this pi 1, this stack has automorphisms. Okay. But it is eventually truncated because X is quasi-smooth. So the fact that X is quasi-smooth implies truncation. And the map MF is actually trivial on all pi n sheaves. All homotopical information is trivial except in degree 1.
Sorry, do you consider only quasi-smooth? Because
Yes,
I somehow lost in the assumptions.
Because X was -1 shifted symplectic derived scheme, and -1
scheme.
right. Scheme.
Okay.
Yes. So it's
because you want to recover Joyce, whatever.
Yes. Yes.
Okay.
So so this is the intermediate results we have so far, and the idea where we're writing down that explains what the idea I was telling you before, is that if you go a bit further, not just quotient by the action of quadratic bundles, but you impose A1 invariants on morphisms, on automorphisms, meaning that you ask for any 2 automorphisms under a certain condition to be related by a family interpolating between the 2, then what you get in this quotient is exactly X. So in a way, it gives a universal property for what Joyce does. and it helps to glue MF. We don't have any work to do. The factorization comes automatically because we are forcing in both cases a quotient by the action of quad and this A1 invariance that exists already. So in order not to build the homotopy ourselves, we prove this result. So so this is an open question. I just put it here. I hope to have some feedbacks. So it's what happens through the mirror symmetry in this case. We know that LG pairs have mirrors. So can we relate what we're doing here to what is happening in the mirror to the LG pairs? That's something I've been trying to learn from people and to see if we can say something about this. And I'm sorry because this is the end of the talk and I already went too far in my time. I apologize for my for going over time. Thank you for your time.
All right, thank you very much. Yeah, that's okay to go a bit over time. So questions or comments?
So you mentioned that in the -2 shifted symplectic, you also got this local model through this foliation plus exact structure.
Yes.
So would you be able to like kind of do what they trying to do, right? Get like a fundamental class or something?
We didn't look at that. The only thing we tried to do so far was to check that this definition gives back the local model. The gluing, we didn't look at that.
Okay.
Yeah.
By the way, there was kind of few recent papers by Adil Khan, who constructs, I believe, at least he told me that he was able to construct the perverse sheaf for DG stacks. I don't know.
Is it out already?
Something is out, but I'm not sure that the full, I mean, the whole, I mean, he had a kind of a big program of constructing, I would say, virtual fundamental classes, but in this DG category settings, and actually it covers, according to him, it covers perhaps everything we know, like Gromov-Witten, for example, Gromov-Witten over finite fields, Donaldson-Thomas invariants, and if you mentioned, I don't remember categorification, but the homological whole algebras, that's for sure. As for categorification of Kochas, I'm not sure that, but maybe he also did, because I remember him mentioning something like categorification of the category of perverse sheaves. Yeah, anyway, there is another language. I didn't have time to read it, but it's kind of, at least some of the papers of him with collaborators, maybe without, they already in the archive. At least this derived intersection theory paper, I believe it is in the archive.
Yes, this is one, yes.
Yeah, Adil Khan. And he announced some joint works with other people about application of that formalism to cohomological whole algebras, I believe with Latintsev, maybe with some other people, I don't know, maybe with Boyka. Anyway, some people affiliated with Joyce. Yeah, but actually concerning, if we kind of do not consider categorification, like goes to the category of matrix factorizations, then the big part of it, as far as I can say, it's already in our paper with Maxim in a baby form, because we did not use the language of shifted derived symplectic stacks. But we considered, I believe, the main example which appears in the nature, the stack of objects of the, in our case, it's -1 shifted, but the stack of objects of 3D Calabia category. But we make remarks in that paper about many generalizations, including to n-dimensional Calabia categories, which means like shifted symplectic stacks of other dimension and other degrees. Also, like these two torsions and lifted, the two torsion which you mentioned, and then it's also in our paper, as well as quadratic line bundles. And the reason is quite simple, because we want to define the sheaf of vanishing cycles, and the ambiguity, as in your example, it's just adding the quadratic form.
And actually, you have something else I would like to understand a bit better, actually, which is the relation of all these to the exponential motives, which is mentioned in your paper.
Yes. Well, it's pretty straightforward, but as in your paper, I mean, the big advantage of your work and some preceding work of Joyce with other people is that there is a language, there is a language. So the definition, I mean, the relation to exponential motives, naively, it's very simple. You have a function on side, and on the right, you take the direct image of the constant sheaf, and you think of it as and it defines you an object in the category of whatever mixed Hodge modules, some exponential Hodge structures. So there is a kind of a toy model example, and then if you have some machinery in your disposal, then you can build the whole theory around it. Because this example, like in our paper on Koha, on cohomological whole algebras, it contains basically kind of everything, the essence of what's going on.
Yeah.
But in a smaller generality, of course, because we did not kind of have a goal to construct a theory for derived DG stacks. I mean, that's yeah. So this is one remark. This categorification. I have a question. There were papers. This guy also gave a talk here at a seminar. Tudor Padurario, a student of, I think, of Andrea Kunkov, and he considered categorification of Koha maybe not in that generality as you did, but in a special example. Maybe even for quivers with potential, but actually, but in fact, he upgraded it to the category of matrix factorizations.
I don't know about this work. What is his name?
Padurario. As you, I don't know whether I can write it down. Yeah, Tudor Padurario. Let me see. Maybe I have precise.
Can I stop sharing my screen? Is it okay?
Yeah,
like
that's
I can
okay.
share. Okay, thank
Padurario. Also, Padurario, I found, okay, he writes, I found that he writes papers now jointly with Yukinobu Toda.
Yeah, exactly. I know
categorical, and again, they're kind of geometers, so they do not need that big generality. But anyway, it's something about -1 symplectic stacks. Yeah, so okay, so if you know him, then probably, or at least his papers, yeah, there are some of them. Yeah, so yeah, it's quite, and there are some other, I mean, plenty of them. I don't know, maybe Latintsev and some other. There is this huge categorifications of Koha, and Koha should be an object of the category of exponential Hodge structure in general, or whatever you. There is this. There are papers by Mario Porta.
Yeah, Mauro.
Mauro Porta with Sala, and maybe with Schiffman, and maybe with some other people, but he is a driving force. Porta is a driving force on DG side, side of the story, and they categorified Koha. And so I believe this also is related, because, you know, Koha is just K0 of some category, and so so it's very nice, very nice. So it's so I hope your paper will appear soon.
Yes, thank you. I hope it will appear soon too. We are trying to finish this last section.
Yeah, but concerning, I understand that you have kind of, you have some language, you learned it, and this language kind of, it's adequate, it describes exactly what's going on. But I believe that our paper, these two papers with Maximum 2008, which I'm not sure anyone really read carefully except a couple of people, which contains a lot of things which later people just spelled in the language of shifted affine, shifted derived algebraic geometry. And second, this paper on Koch. So anyway, more questions? Okay, if there are no more questions, so thank you very much for the talk.
Thank you, and thank you for your comments.
And so I'm looking forward to your paper.
We'll try to work this out fast, and I'll send it to you when.
Thank you. Sure. Okay. Bye.
Okay. Thank you. Bye.